Hello all. Today we're talking about functions. The reason we talk about functions is because these are things that we use in real life. Many events that occur in everyday life involve two related quantities. For example, to operate any machine, you insert the money and make a selection. The machine gives you the selected item and any change due. Once your selection is made, the amount of change you receive depends, and I want you to remember this word depends, on the amount of money you put into the machine. Two things you should be able to do by the end of this video. The first, describe subsets of real numbers. The second, identify and evaluate functions and state their domains. The first key concept we're going to talk about is the real numbers. The real numbers consist of the natural numbers, the whole numbers, the integers, the rationals, and the irrationals. I'm going to start with the rationals. We symbolize the rational numbers with a Q. They are numbers that terminate or repeat in decimal form, or they are written as a ratio of two integers. They can be either both positive or negative. Within the rational numbers, you have the integers. If over here in this Venn diagram, you see this circle inside this square Q. These are the integers. Integers are negative and positive whole numbers, including 0. Inside the integers, we have the whole numbers. The whole numbers are 0, 1, 2, 3, etc. Within the whole numbers, we have the natural numbers. And the natural numbers are 1, 2, 3, 4, etc. The symbols we use for natural numbers is an N. Whole numbers is a W. Integers is a Z. Don't ask me why. It's not I, but it's Z. We just have to remember it's Z. The irrational numbers are I, and then the rationals again are Q. Now, I'm going to do a couple of examples that were not from the PowerPoint so that you can get an idea of this thing called set builder notation. We use set builder notation to describe a set of numbers. The first set of numbers that I'm going to write out are. Oh, I need a pencil. We put it as a set of numbers. And a set of numbers always has a brace. And the first number, we're going to start at 8, and then 9, 10, 11, etc. And then we close our brace. All sets that you write have to be written inside braces. Now, if we're going to write this is just a set of numbers. If we're going to write this set of numbers into set builder notation, again, we start with a brace, and then we're going to put x such that x is greater than or equal to 8. Now, we have to put a condition on here. The condition has to say that we're not dealing with any decimals, so we're not going to be dealing with rational numbers. So we have to say that these have to be in the whole numbers. So we have to say x is an element, and that's what this symbol means, element, of the whole numbers. And we have to end that with a brace. Now, some of you could be asking, well, aren't those integers? They are, but we always use the most specific set. Now, we could have used integers, but we know for a fact we're not dealing with any negatives, so we don't want to use integers. We're going to stick with what we know. Now, we could have said natural numbers, and I would have been okay with natural numbers. Now, let's do another example. Let us look at when we don't have a set of numbers, such as x is less than 7. Now, if we're going to write this in set builder notation, this is really easy. Set builder notation is just going to be the brace, and then we're going to put x, and this line here, that line means such that. So we got x such that x is less than 7. Now, this we see that x can be less than 7. That doesn't mean it can't be 6.5 or 5.39 or even pi. So we have to say that our stipulation is that x has to be an element of the real numbers. And then we close the brace. So this shows us, we started with a list of numbers. And I showed you how to write that in set builder notation. Then I showed you a condition saying that x is just less than some number. You'll notice, I want you to notice that this is this right here. Those are the same things. Whatever we had up here just gets written in right after the such that. Those are the easy ones. Now, to deal with something a little harder, we're going to deal with all multiples of 3. So all multiples of 3. Now, if I'm going to write this in set builder notation, well then, let's think about that. All multiples of 3. Well, there's 3, and there's 6, and 9, etc. And there's all those numbers. Well, when we do this, we have to start with our brace, and we're going to put x such that x equals 3 times n, where n is some integer. Close. Now some of you are saying, where did this n come from? We have to put this n in there whenever we're talking about multiples. Because now if I look at n and I plug in, I don't know, let's say 1, well then 3 times 1, well isn't that a multiple of 3? Yeah, so that fits with what x can be. Does that work for 2? Yeah, 2 times 3 is 6. 6. Sure, we're good. Alright. So these will work. These 3 methods, which is the 3 things that you're probably going to see in your homework, a list of numbers, set builder notation for that. Of an inequality, and that's what this is. This is an inequality, x is less than 7, and it's set builder notation. And then words saying all multiples of 3. Now you can put in 5, 9, 7, whatever you choose, but this is the set builder notation for that. The other type of notation that you're going to see, other than set builder, is something called interval notation. Now, you should remember this from Algebra 2. Interval notation, I use that quite a bit. Interval notation is definitely my favorite type of notation to write things in, write sets of numbers in. With interval notation, that's where you're going to use the parentheses and the brackets. For example, if I have -8 is less than x, which is less than or equal to 16, this is my inequality. I can write this in set builder notation, or I can write this in interval notation. So I'm going to do both, just to give you a little more description with the set builder. So starting with set builder, I'm going to put x such that, now remember what I said about inequalities. Whatever the inequality is, I take it and it goes right here. So I'm going to put -8 is less than x, which is less than or equal to 16. Okay, there's no stipulations on decimals or anything, so we're going to say x is an element of the real numbers. Close the brace. Okay, here's your set builder notation. Now let's take a look at interval. Interval notation. Now we can't, according to this, this doesn't equal -8. If it equaled -8, we would have this negative underneath here. Well, it's not there, so we know the x cannot be -8. So we will start with a parenthesis, meaning not equal to, and then we put -8. And that's our lowest number. We always put our smallest number first, and then we put our largest number that x can possibly be. In this case, it's 16. Now, we see that there's a line underneath this inequality symbol, therefore it's equal to. So instead of a parenthesis, I have to put a bracket. This is interval notation. Set builder, interval. So let's give us another example. X is less than 11. Putting this into interval notation, my lowest possible value, since there is no lowest possible value, is going to be negative infinity. Negative infinity all the way up to, and then we look at this, the highest number is going to be 11. There's no equal sign, so we put a parenthesis. One more example. X less than or equal to negative 16, or X is greater than 5. Now when I look at this, I have this or in here. That changes things just a little bit. Still pretty simple, but we need to include something, and I'll explain that in just one second. So when I look at this, the lowest possible value is still going to be negative infinity up to, and then it says negative 16. Line underneath it, bracket. Now this or symbol, this right here, to simplify or, we put union. It's just a U. It looks like a U. And it is read as union. And then we start up again. X has to be greater than 5. So 5 to infinity. This is your interval notation. Now if I were going to put this into set builder notation, it would be brace. It would be X such that, and then remember it's an inequality, so I just put in X is less than or equal to negative 16, or X is greater than 5. Stipulation, X is an element of the real numbers. Set builder, or interval notation. Next, we're going to talk about the actual key concept of a function. F from set A to set B is a relation that assigns to each element X in set A exactly one element Y in set B. Okay, so what does this mean? Oh my gosh, I read this and what's going on? And all this is saying is that for each thing that is in this set A, it maps to exactly one thing over here. So 1 goes to 6, 2 goes to 8, 3 goes to 8, and 4 goes to 8. Now you'll notice that this has 2, this 8 has 2 and 3 going to it. That's okay. What we can't have is you can't have 2 going to 8 and 2 going to 7. This is kind of a break. This is breaking the rules. Okay? Therefore, it's not a function. Now, the domain is all the elements that are going to be in this set. The range is all the elements that are used in this set. So 6, 8, and 9 are the range. 1, 2, 3, and 4 are the domain. Okay. So there's 4 different ways you can identify functions. The first is verbally. A sentence describes how the inputs and outputs are related. So a sample would be the output value is 2 more than the input value. Now your inputs, another name for input is domain. Another name for output is range. Okay, second way, numerically. A table of values or a set of ordered pairs relates each input with an output value. So far we've talked about domain, and we said domain, another name for domain, is input. Also, X, also independent variable. Yes, I know my handwriting's messy. It's hard to do it with this tablet. Okay. Now, we've also talked about this range thing. Range, another name for range we said was output, also known as Y, and this is the dependent. Remember how I said remember the word dependent or depends? And the reason this is called the dependent variable, dependent. The reason this is called a dependent variable because it always depends on whatever your domain value is, whatever your input value is, whatever your x is. Okay? So now with that being said, if we're looking at a numerical table of values or a set of ordered pairs that relates each input with an output value, an example of this is simply an XY chart. An XY chart, yes. Okay. The third way you can see this is by graphically points on a graph in the coordinate plane represents the ordered pairs. So the pairs we just put up here, we can put that in a graph. And that will give us another way to represent a function. So we got the y and the x, and then we got these points. Those represent a function. This is called a discrete function. The discrete function because there's breaks in the function. Now, a continuous function, we'll put that in orange. A continuous function is just going to be one solid line or one solid parabola or any other type of graph that is continuously. There's no breaks. Finally, algebraically, an equation relates the x and y coordinates of each ordered pair. This is what we're most used to seeing. Simply y equals mx plus b. There's a function. It's a function of a line. Now, instead of using y, we're going to start using this thing called function notation. F of x, and same thing, mx plus b. This is the function in terms of x. Just a name. Another way to say y is f of x. Another way to say f of x is y. Those are interchangeable. I want you to remember that. Vertical line test. The great thing about the graphs of functions, we can see if it's a function really quickly. And the way we do that is something called the vertical line test. Okay, and what this says is I will have this vertical line, and this vertical line, if it hits more than one point at any given time, then it's not a function. That's all the vertical line test says. So when I'm looking at this, example 3, I'm going to put a graph up here, and I'm going to show you how we use the vertical line test. So I'm going to have this graph. Now, what I'm going to do is I'm going to cover that up, and here's your vertical line right here. As we drag this along, will the graph that I put in here ever touch it at more than one time? And the answer is no. It won't. So let's see what a graph looks like that does touch it. We'll make it green, and we'll put this. Now, when you move this vertical line across, oh, it touches twice. It touches right here and right here. So it touched two times. Therefore, this green one is not a function. For this, and really what it's telling you is this x value is going to two different y values. Remember that this right here, where we had this number 2 going to 8 and 7? Well, broke the rules. Same thing here. It's breaking the rules. This x value has two separate y values. Function notation. So I talked to you about a function notation a couple minutes ago and how it's interchangeable with y. So now we're gonna see how function notation is used. So typically you're going to be given some type of function that says g of x, and this g just means it's not f, it's g. It's just a name. So g of x equals x squared plus 8x minus 24. Okay? And they're going to ask you to find the value of each function. So, and then they're going to give you, they're going to say, for the first problem, they want to see g of 6. Now, all we do is we take this 6 and we put it in place of x. That's all we do. Wherever we see an x, that's what we put it in. We put the 6 in place of. So we're going to have 6 squared plus 8 times 6 minus 24. So then I've got 36 plus 48 plus 48 minus 24. And then we just continue to simplify this. And when we simplify it, we end up with 60. So g of 6 equals 60. Now, B. Occasionally they might ask you, instead of putting in a number, they will ask you to put in another variable. For example, they could ask you for g of h. What is g of h if g of x is that function up there? Well, this is really simple. We just take and we plug in h wherever there's an x. H squared plus 8h minus 24. Can't combine, and there's no like terms there. We're done. Moving on to the next one. And sometimes they could ask you to put a completely different expression in. So g of 5c plus 4. Well, guess what you do with the 5c plus 4? Yep, you're right. You put it in place of x. That's all we do. So putting it in place of x gives us 5c plus 4 squared plus 8 times 5c plus 4 minus 24. Now, we're going to have to do some calculations here. We're going to have to expand that out so that we can see if it simplifies. Now, so many of you do not make this mistake. This 2 does not, let me repeat, does not just get put into that. We have to take that and expand it out. 5c plus 4 times 5c plus 4 plus 8 times 5c plus 4 minus 24. So now I take a look at this and I say, oh, 5c plus, so now I have to, and you guys can call it FOIL, I call it the distribution property. You're just going to distribute it throughout. So that gives me 25c squared plus 20c plus 20c plus 16. I'm going to distribute the 8, 40c plus 32 minus 24. Ooh, barely, almost ran out of room there. So now I clean this up, combine like terms, and I end up with 25c squared plus 80c plus 24. Yeah, 24. Alright. This is your final answer. You cannot clean this up anymore. There's no like terms. People do not, this is FST, do not combine 80C with this 25c squared. Okay. All right. So now, next we're going to start talking about, we're almost done. We're going to start talking about domain and range. Domain and range of a function. Domain is the x values, range is the y values. I mentioned that already. Now, there are times where we have the domain has to be restricted. Typically, you don't see a lot of restrictions on domains until you start dealing with some more advanced functions. One of the more advanced functions is the hyperbola. You guys should remember hyperbolas from Algebra 2. They were the ones you guys didn't like. So if I'm looking at f of x equals, and I'm going to say 2 plus x over, let's say x squared minus 7x, we'll say, yeah. So looking at this, we have to look at this and we have to say, okay, when are we going to have problems with this? When x is what? Well, the only time we ever have a problem with when we have something like this is when there's a 0 in the bottom. Big message. Can't divide by 0. So with this in mind, we say, well, there's x's in the denominator. Well, what would x be to make this denominator 0? So we have to literally take it and figure it out. X squared minus 7x, and we're going to set it equal to 0, because that's when there's a problem. And then we factor this, so we got x minus 7 equals 0. Looking at this, I'm going to set each one of those equal to 0. X equals 0, or x minus 7 equals 0. So then x equals 7 or x equals 0. Here is the restriction on your domain. And we actually write this in either set builder notation or interval notation. In set builder notation, and yes, you must write it in set builder notation or interval notation, x such that x cannot be 0, x cannot be 7, and x is the element of the real numbers. There's set builder, here's interval. Okay, interval notation. Negative infinity up to 0, union 0 to 7, union 7 to infinity. What this union says is it stops and then starts again, and then stops and then starts again, and keeps going on forever now. Okay, set builder, interval. Your answer has to be one of these two if it's asking for the domain. We will talk about range at some other time. The next type of problem, so there's where you have one type of problem. You have one type of problem when you deal with hyperbolic functions or rational functions. The other type of problem is when you have square root functions. So g of t equals say square root of t minus 5. Now, what you do know, you know that you can't take the square root of a negative number. It's not a real answer. You guys saw that in Algebra 2. So what we're going to do is we're going to say, well then, t minus 5 has to be greater than or equal to 0. We have to set it greater than or equal to 0. Now solving this, we see that t has to be greater than or equal to 5. Because if it's not greater than 5, this becomes a negative number. So we write this in set builder or interval notation. Set builder, t, such that t has to be greater than or equal to 5. T is an element of the real numbers. Interval case, it's 5. So, and since it can equal 5, we put bracket 5. And then we go to the highest possible number, which is infinity. Can't equal infinity, so it has to be a parenthesis. Then we have the last type, which is a really scary type. This one, we've got h of x equals 1 over square root of x squared minus 9. Now in this case, we're looking at this, we can't have this be 0, but it has to be greater than 0 too. This radicand, and that's what this portion is called. The portion of the radical, it's called the radicand. So we have to take that, and this time we're going to say x squared minus 9 has to be greater than 0. We can't put the equal to this time, because if it equals 0, then this whole thing bottom would be 0, and then we have a problem with the fraction. So now we just solve this. We say x squared has to be greater than, we move the 9 over, so 9. So we have this x squared is greater than 9. So when I'm looking at this, when I take the square root, it becomes x is greater than plus or minus 3. Now, the problem with this is, as soon as you do a plus and minus here, this sign has to shift. This has to flip around. But it only flips around for the negative. So, we actually have two possible answers. X is greater than 3, or x is less than negative 3, because we changed the sign. So when we're putting that in interval notation, we're going to say my lowest possible value is negative infinity to negative 3 union 3 to infinity. The last topic we're going to talk about today is something called piecewise defined functions. These give people such a hard time. Piecewise defined functions are pieces of functions. For example, if I have a graph, I could put in several different functions across the spectrum of the domain. For example, I could have this function, and then followed up with this function. Okay, you'll notice that these two don't really go together, but they are both on this graph. This is a piecewise defined function. Okay, they can be anything. They can be of any type. I could have like this, and then a line going straight down that way. Typically, when you have piecewise defined functions, you have endpoints at their graphs. They're not really continuous. So here's an example. Okay, the average maximum height of children in inches as a function of their parents' stop. Now, what did that say? That's what we have to try to get you guys to with these story problems. Read the first part, stop and think about it. The average maximum height of children. Okay, in inches. Okay, so we're looking at the height of a child in inches. And it's a function of their parents' maximum heights in inches. Okay, so that means, when I'm thinking about that, that means, okay, the child's maximum height is going to be a function of their parents' maximum height. Okay? And it can be modeled by the following piecewise function. So, as soon as I see this modeled by the following, I immediately look down and see the function. Okay, the function's there. Cool. We don't have to come up with it. They gave it to us already. That's awesome. Now, find the average maximum heights of children whose parents have the given maximum heights. Okay. So they're asking us to find the average maximum heights of children whose parents have the given maximum heights, and there's some numbers that I'm going to give you that those will be the parents' heights. It says use h of x where x is the independent variable representing the parent's height. Okay, we said independent variable x. Keep that in always. That's always going to be the case. X is always the independent variable. And h of x is the dependent variable. Remember what I said about h of x? It also could be written as y. So y is the dependent variable representing the child's height. All right. So now we're going to look at this and we're going to say, oh, here's my function. Good. You'll notice that there's three different areas. So it's 1.6x minus 41.6 if x is between 63 and 66 inches. The function is 3x minus 132 if x is between 66 and 68 inches. And finally, 2x minus 66 if x is greater than 68 inches. Wow, that's tall. All right, so now we're going to say, what if we're looking at a parent's height, h of 67. So when I see this, I look at it and I say, all right, well, 67, well, that falls in here. So I'm going to use this function. So then I'm going to say 3 times 67 minus 132. And I'm going to solve this, and I get, or simplify that, and I've got 69 inches. So we would expect the child to be 69 inches. What about h of 72? So I look up here, 72. Oh, well, that falls in the third one. So I would say 2 times 72 minus 66. And I simplify that, and that simplifies to 78 inches. So, let's recap. We have talked about interval and set notation. We have decided what a function looks like. We have used the vertical line test. We have found domain of functions algebraically. And we have talked about piecewise defined functions. You should be ready to work on your homework. If you need more help, go back through this video or check out the PowerPoint. You have to check out the PowerPoint anyway because you have to fill out your study sheet. Thank you, and we'll work on the homework in class tomorrow. Thank you, guys.